this is example 6.8, motion on a curved path. And it says, a family picnic, you were appointed to push your obnoxious cousin Throckmorton in a swing. His weight is W, the length of the chains is R, and you push Throcky until the chains make an angle theta with the vertical. To do this, you exert a varying horizontal force that starts at 0 and gradually increases just enough that Throcky and the swing move very slowly and remain very nearly in equilibrium throughout the process. What is the total work done on Throcky by all the forces? What is the work done by the tension? And what is the work you do by exerting force F? Okay. All right, so the free body diagram is going to look something like this. Here's your cousin. You've got, these are the chains, that's T. So you've got this guy. Oops, that's the vertical. T cos theta. This is theta. And then you've got the force here. This is going to be T sine theta. And that's his weight. We could sum up the forces in the X and the Y direction. So sum of the forces in the X equal F minus T sine theta. That's going to equal 0. He's in equilibrium. And some of the forces in the Y are going to equal to T cos theta minus W equals 0. All right, now solving for F, I'm going to get F equals T sine theta, and T cos theta equals W. So I'm going to solve for T now. T equals W over cos theta. Now I'm going to eliminate T and say F equals sine theta over cos theta times W, the weight. All right, from our equation 6.2, we know that this work with a varying force is going to equal to the force Fs times the cosine between them, cosine V. So we're going to go ahead and substitute. We'll get work equals F. Oh, we've redefined F as W sine theta over cos theta times cos, and it's going to be theta, the angle between them. And then the distance he goes is going to be the arc length times the radius. So we're going to get R e theta, and this is in radians. We're going to integrate from 0 to theta. Let me pause and clean up my board. All right. I'll bring it over here. Oops. The pen. We've got work equals the integral from 0 to theta. I'll go ahead and pull out W. Well, let me just go ahead and move this. Let me pull out the weight. This is the weight, by the way. The weight and the radius we have from 0 to theta. And these guys are going to cancel of sine theta d theta. And that's going to be equal to the negative WR of cos theta from 0 to theta. And then we've got negative weight times the radius of cos theta minus 0, because that's what 0 is. We're just going to go ahead and rearrange this to be WR. Oh, sorry, this is 1. Cos of 0 is 1. My bad. 1 minus cos theta. And that's your work. And for the work done by the tension on the chains, that's going to be 0, because that's perpendicular to the direction of motion. And let's see, they're calculating the work done by, okay. The net force on him is 0, and the integral of the net force is 0, so the total work on him is 0. So this is the work done by the force. Okay, 6.9 is force and power. Power and force. And it says, each of the 4 jet engines on Airbus A380 airliner develops a thrust of 322,000 newtons. So that's your force. What is the airplane, when the airplane is flying at 250 meters per second, what horsepower does each develop? Okay, so first we need to know the power, and we're going to solve that in watts. Power equals force times velocity, because it's work over time, and that works out to work over time. So this is going to be 3.22 times 10 to the 5th newtons times 250 meters per second. And we're going to get 8.05 times 10 to the 7th watts. And now converting that into the horsepower, I know that 1 horsepower equals 746 watts. So just go ahead and divide by 746 watts. And that will give me 108,000 horsepower. All right, 610 is a power climb. A 50-kilogram marathon runner runs up the stairs to the top of Chicago's 443-meter tall Willis Tower, the second tallest building in the United States. To lift yourself to the top in 15 minutes, what must your average power output be? Express your answer in watts, kilowatts, and horsepower. All right, her work is going to be equal to that change in potential energy. So work equals mgh. And so what did we have? M is going to be 50.0 kgs. G, of course, is 9.8 meters per second squared. And H was, let's see, 443 meters. And this is going to give us 2.17 times 10 to the 5th joules. And she does this in 15 minutes. So 1 minute is 60 seconds, so 15 times 60. And that's going to give us, let's see, 241 watts. And then I'm supposed to express it in horsepower. Kilowatts, I'm gonna, this divided by 1,000 equals 0.241 kW, kilowatts. And for the horsepower, 241 divided by 746, I think, what was it, am I supposed to express it? Yeah. That was 746. Oh, wait a minute, no. 1 horsepower, 746 watts, so this is, yeah, 746 watts equals 0.323 horsepower. There you have it.